Now that we have an understanding of sigma notation, we're going to put that together with what we know about Riemann sums and write our Riemann sums in sigma notation. So we, in non-Riemann sum notation, wrote f of x k star times delta x, etc. And so if we do it in sigma notation, we're just going to go from k equals 1 to n of f of x k star times delta x. Now, we can modify that to make sure that we can talk about xk star specifically in terms of left, right, and mid. So that's what we're going to do next, is how do we figure out the value of xk star. So left, right, and mid, we again have our delta x. And because this delta x is a constant, we can actually factor it out to the front, which we've done before. And so down here you see it's factored out. So we have our delta x factored out. And then we have f of, and we have our definitions of xk star. So our xk star for the left Riemann sum is going to be a plus k minus 1 delta x. Okay, so I want to be left. I want to start at a and then go to the next interval, but I want to have a be the first one. That's why we have k minus 1 right here, because when you plug 1 in for k, you get 0, and so a is the first point. Then when k is 2, you have a 1 times delta x to get to the next one. So that is going to be the thing that gets plugged in to f of x. That is our xk star. Now, if it's a right Riemann sum, you don't want to start at a. You want to get all the way to b. So you immediately add on a delta x when k is 1. And so that's what we would do for the rights. So for the rights, we plug that into f. Now for the mids, it's a little more complicated, but I want to go halfway to k the first time. So k minus half is actually 1/2. And so I'm going to put that in the first time. And then when k is 2, I'm going to go 3/2. So we're going to go 3/2 from the original, which is 1 more than the first half. And so that is the xk star value for the midpoints. So we plug that into f. Okay, so let's take a look at an example using Riemann sums in sigma notation down here for the function, same function, 3 square root of x that we've used before, and actually the same intervals, so we're going to get the same answer. So let's just double check this in Riemann sum notation. So r sub L is equal to, okay, so we already did our delta x, but just as a reminder, we can put it back up here. Delta x is 16 minus 4 divided by 6, so that was 2. So we're going to have our 2, our delta x, times the sum from k equals 1 to n, but n is 6, so it is 6, of f of, I'm just going to write f of first, and then we'll actually use the function f in a moment, but f of, if I'm doing the left, a is 4. Again, these were our ends of our intervals, so those are a and b. So a is 4 plus k minus 1 times delta x, and again, delta x is 2. Okay, so that goes in to the function. So this is going to be 2 times the sum of k equals 1 to 6 of, the function is 3 times the square root of x, so 3 times the square root of 4 plus 2k minus 1. All right, that's the Riemann sum that we need to evaluate. We'll do the left one, and then we'll go back and write the ones for the right and mid. All right, so first, come on, Desmos. First, we have to do 2 times the sum from k equals 1 to 6 of 3 times the square root of 4 plus 2 times parentheses k minus 1, and we have a left sum of 105.876. Now, like I said, we already did this one a couple pages ago by hand without the Riemann sum on page 22, and we got the exact same thing working those 6 pieces by hand. Okay. Now, working 6 pieces by hand wasn't that much work, but if I had to work 12 pieces or 20 pieces or 500 pieces, the Riemann sum is going to be essential. So it works, gives us the same thing even for a small number. Let's double check it and keep working for the next two. So that's the left. Let's look at our right. Okay, so delta x is 2 times the sum from k equals 1 to 6 of first f of a, which is 4, plus k times delta x, which is 2. Okay, so this is 2 times the sum, k equals 1 to 6 of f, which is 3 times the square root of 4 plus 2k. That's the right Riemann sum. If we go back and evaluate that, I'm just going to modify this line. We get 117.876, and I believe that's the same thing that we had before. You guys can check that. It sounds familiar. And then our mid Riemann sum is going to, again, start with delta x. So 2, delta x is 2, times the sum from k equals 1 to 6 of f of a is 4, plus k minus 1/2 times delta x, which is 2. So this is 2 times the sum k equals 1 to 6 of 3 square root of, and inside that square root I have 4, plus 2 times k minus 1/2. Just writing the 2 first because it's a coefficient. See what we get. And it should be the same thing. I think it was 112, something like that, when I did it on the other side. So 2 times k minus 1/2. Yep, oops, wrong parenthesis. There we go. And like we got before, we have 112.062. And I believe that's what we got when we did the midpoint by hand as well. Now we're going to do it again, but we're going to increase the n value. I should have just kept them all separate, but that's okay. We're going to increase the n value. Recall that a was going to be 4, and delta x is defined to be 16 minus 4 over n. N isn't going to be 6 anymore, so I can't use the 2 that I got by plugging in 6 here. Instead, I'm going to use 12 over n. So I'm going to redefine the left, right, and midpoint sums here in terms of n. Okay, so the left, it has delta x first, so it has 12 over n. Then it has times the sum from k equals 1 to n of, and then we can, what do we want? Let's go ahead and put the function in. So it's 3 times the square root of, and remember that it is supposed to be of a, which is 4, plus k minus 1 times delta x, so plus 12 over n times k minus 1. That is our left generalized. So a few things changed between this page and the previous. Mostly what changed was, instead of having the 6 for delta x, we now have 12 over n, and instead of 6 for n, we now have n. Okay, I'm going to write in the ones for the other two as well, and then we can calculate the sums. So the right, 12 over n, sum k equals 1 to n of 3 times the square root of 4 plus 12 over n k. The same 3 changes here. We changed delta x and we changed n. And then for our midpoint, 12 over n times the sum from k equals 1 to n. Inside the function, we have 4 plus 12 over n times our k minus 1/2. And again, the same 3 changes, of course. Changed n, delta x, and delta x again. All right, so now I'm going to type these 3 lines, and we're going to actually keep n general. so I can let it vary. This is where decimals comes in real handy. Okay, so I'm going to let n be n. I'm going to have to add a slider for it. Or maybe I'll add a slider in the summation. That'll work. So the sum from, I want this to be k, equals 1 to n of 3 times, and that's where I'm going to add the slider for n. I'm going to pull it above. There we go. 3 times the square root of 4 plus 12 over n times k minus 1. This is going to be the left. I'm going to go back to the front of this. I didn't type in the 12 over n because I didn't have n defined as a slider yet, but now I do, and so I've got the whole thing right here. So I'm going to call this r sub l equals, so it's going to define what r sub l is for me. And then I can do r sub r and define that as 12 over n times the sum from, make sure you have k equals 1 to n of 3 times, my function is the square root of 3 square root of a, which is 4, plus 12 over n k. Okay, now this is just an r value, an n value of 1 right now. We're going to let that n slide and watch the sums change. And so last we have our r sub m. It's going to be equal to 12 over n times the sum, k equals 1 to n, of 3 times the square root of 4 plus 12 over n times k minus 1/2. First thing I want to do before I look at what my goal is I want to try an n value of 6 and just make sure that we have the 3 things that we were hoping to have. We do the 105, 117, 112 that we saw on the previous page. Now we want to do 50. So I'm going to start with 50 and we're going to step this by 50 as well. So I'm going to go from 50 to 200 with a step of 50. Okay, so at 50 I can fill in the values, and again I was picking 50 with a step of 50 so I can go 50, 100, 150, 200 to get these 3 values filled in. So 50, we have 111.27, etc. We have the 112.718 and 112.0089. Those values are already written in for us. So if I increment this to 100, I'm going to fill in my table here. For 100, the left is 111.63955. The right is 112.35955. And the mid is 112.000225. Now if we increase, we can see what 150 would be. I'm going to increase all the way to 200. So 200, I have 111.81989, 112.17989, and 112.000056. Okay, so we've got these filled in. It doesn't matter if I'm looking at the left, the right, the mid, they're all getting closer to 112. So 111.8 gets close to 112, 112.1. The left ones are increasing. They were all underestimates, remember? The right ones are decreasing. They were all overestimates. And the midpoint had a little under and a little over. So based on the table, we think that the exact value of that area is probably going to be 112 square units. And so we're just watching the pattern. These are increasing up towards 112, these are decreasing down towards 112, and these are getting closer and closer to 112. So 112 square units is going to be an approximation for the exact. So by increasing the number of rectangles going to 200 rectangles. So there's no way we're going to write down 200 sums and add them all up by hand, but the sigma notation lets us do that efficiently. Okay, visualizing above what's happening to the width of those rectangles, and so they're just getting smaller and smaller. You have the same space that you had before between A and B that we put 6 rectangles in before, but now you have to fit in 200 rectangles, so they are super, super, super narrow. I don't have their tops drawn, but they are super, super narrow, and so the width of the rectangles is shrinking to 0. It is approaching 0. So the width is delta x. Delta x is approaching 0. And so if we really, really want to look at this in terms of limits, we could do a limit of the summation notation as delta x approaches 0 of one of ours, so like r sub l or r sub, they should all equal at that point, so it doesn't matter which one, because if I let delta x approach 0, they're all going to converge on the same value.